how to move from polygons on the surface of a sphere to polyhedrals, or polyhedrals to polygons on the surface of a sphere. So the basic process is to expand any convex polyhedra to the surface of a sphere of radius 1, say. You can just define the radius to be 1, is place the polyhedra in the center of the sphere. For each polyhedral vertex, draw a line from the center of the sphere that intersects the vertex and the surface of the sphere. And for points joined by edges on the polyhedral, join the corresponding points by arcs of great circles. So basically it's a three-step process, and it looks something like this. Here you have a polyhedral, looks something like this. Then you place it in the center of the sphere, and you draw lines out to the surface of the sphere, and you get if it's connected by an edge, if the two vertices are connected by an edge on the polyhedral, then connect those intersecting points on the surface of the sphere with the arc made from a great circle, the shortest distance between 2 points on the surface of a sphere. And what you end up with is this three-dimensional figure. So here I specifically showed the three vertices V1, V2, and V3 on the polyhedral mapped out to the same vertices of the same name on the surface of the sphere. So what you end up with is a system of polygons. See, V1, V2, V3 is a polygon on the surface of the sphere. It was the face. It was mapped from the face of the polyhedral that was in the center of the sphere. So basically you have a one-to-one correspondence. You lose a little bit of geometry in the process, but you keep the relationship between the edges and the vertices, and then you're able to use the spherical trigonometry to gain insights about that. So it's basically a three-part process, and what you end up with for mathematical purposes, you just end up with a schematic network of polygons that you can solve relationships between the edges and the vertices and the faces of the polyhedral. Then the next step is to find relationships between the number of faces, the number of vertices, and the number of edges. All right, now that we know how to map any three-dimensional polyhedral to a two-dimensional network of polygons on the surface of a sphere, we go through a process to find the relationships between the number of faces, the number of vertices, the number of edges of any random polyhedral. First, convert the network to a 2D network of polygons, just as we just explained. Define the radius of the sphere to be 1. So in general, the sum of the external angles of any polygons is given by this relationship, 2 pi minus the area of the polygon divided by r squared. And then part 2 just says set or define r equal 1. So the area of the polygon is actually just equal to 2 pi minus the sum of the external angles of that polygon. If you look over the sphere globally, you set, part 3 is to set the area of the sphere, which is 4 pi r squared, or just 4 pi when r equals 1, to the sum of the polygons. Okay, so just index the polygons with j and say there's f number of faces, or f polygons. Here we show 4 of them schematically, and 4 pi equals the sum of the polygon areas. Replace that, each area, with 2 pi minus the sum of the external angles of that specific polygon, and then you look at all the polygons, you just end up with 2 pi f minus the sum of all the external angles for all of the polygons, which is a little bit of an unknown quantity unless you're going to go take your polyhedral and measure the external angles or of every facet or every face or every polygon surface. You know, you're not going to really know what that is, but that gives us one basic equation. We just need to get one more so that we can eliminate this beast here. To get a second relationship between the external angles and the edges and faces and vertices numbers, look at another basic fact. At any vertex, the sum of the internal angles by definition equals 2 pi. Just goes right around in a circle. We can change that to a relationship for the external angles by just noting that the external angles are just the complement of the internal angles. So we can write pi minus alpha k1 plus all the way up to pi minus alpha k sub ek, where this ek is just the number of edges that happen to come into that particular vertex. So we just pick a vertex, call it vertex k, and then call ek the number of edges coming into that vertex. So the relationship is simply summing up pi minus alpha, pi minus blah 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 blah, pi minus alpha sub k ek1. So since you have pi instances, ek number of instances at each vertex, you just get a relationship that's like the sum of the external angles equals ek times pi minus 2 pi. We just don't know how many edges happen to come into any arbitrary vertex, but that's the first step of getting the new equation. So we have a relationship for each individual vertex, call it vk, that the sum of the external angles is equal to the number of edges ek coming into that vertex times pi minus 2 pi. To get an equation for all the external angles for the whole sphere globally, we sum over every vertex k. So for each k, we have this sum, ek1 up to ek sub ek. But the number of vertices, of edges coming into some individual kth vertex, the ek's are unknown. But if you sum over all k from 1 to v, where v is the number of vertices for the whole system, you just get this summation equals this thing that we're looking for, the sum of all external angles for the whole system. Each one individually is ek, the unknown arbitrary number ek at that kth vertex, times pi minus 2 pi. If we sum from k equals 1 to v, we get pi times the summation of all the ek's minus 2 pi v. But the interesting thing about the summation of all the ek's, they're all arbitrary, but the sum over all vertices is just 2 times e, the number of edges in the system, because each edge connects 2 vertices, so essentially each edge gets counted twice in this system. So we can replace the sum of ek, this term right here, with just the number 2e. So therefore, repeating the sum of this mysterious sum of all the external angles then becomes 2 pi e, because we replaced the sum with 2e, so 2 pi e minus 2 pi v. And we can go back to the original equation, which was that 4 pi equals 2 pi f minus the sum of all the external angles. So we just take the negative of this term and say 4 pi equals 2 pi f plus 2 pi v minus 2 pi e. But you can divide out the 2 pi and suddenly you get the equation we're looking for, Euler's formula for any arbitrary Euclidean convex polyhedral, that f, the number of faces, plus v, the number of vertices, minus e, the number of edges, equals 2. Always, always, always. So that's quite an amazing result, and it wouldn't have been possible using Euclidean geometry. We used this geometry on the surface of a sphere. So that's the principal result. Okay, some things covered in this presentation. Spherical triangle is a collection of 3 vertices on a sphere connected by segments of a great circle. Segments of a great circle are simply the shortest distance between 2 points. So that's the natural analogy with a straight line on a plane. The simplest polygon on a sphere is not a triangle but a biangle. That just means great circles cross in 2 points, so you don't have to have a triangle. Placing a triangle in a sphere partitions the sphere into 3 biangular polygons and 2 triangle polygons, so 5 parts naturally. And that's the beginning of the proof of Euler's formula, according to this presentation. The sum of the internal angles for a spherical triangle is alpha plus beta plus gamma equals pi plus the area of the triangle divided by r squared. From this is trivial to see that for a planar triangle the internal angle is summed to pi, because if it's planar then the radius is effectively infinity, the area doesn't matter. So there's something generally vague about having an infinite flat surface, in some sense that's more of a theoretical construction than, say, like the surface of the Earth, which is naturally spherical. So in the real world, it's almost more natural to talk about spherical triangles than it is planar triangles. And then you get this weird kind of relationship, if you think about it, of there's something more vague about it. An infinite radius flat surface, perfectly flat, where the curvature doesn't matter at all because it doesn't exist. Anyway, be that as may, for a spherical polygon, any polygon on the surface of a sphere, the external angle is sum as the sum of the external angle equal to 2 pi minus the area of the polygon divided by the radius of the sphere, r squared. Very interesting. That can be used to show that for any convex polyhedral in 3-dimensional space, the number of faces, f, plus the number of vertices, v, minus the number of edges equals 2. And that's just a simple logical property of the universe we happen to be born into. It might be another kind of universe that could exist, but that's an example of mathematics, in a sense, proving a property of the real world. And another is over here, where we look at this equation, Euler's formula, f plus v minus e equals 2, provides an easy, if perhaps hard to remember, proof, at least I have a hard time remembering on occasion, that there are only 5 possible platonic solids in the universe, because of this easily converts into an inequality based on the number of edges per face and the number of faces coming together at each vertex. So we've basically shown here that f plus v minus e equals 2. I kind of explored the meaning of that formula and the origin of that formula, attributed to this man, the contemporary of Benjamin Franklin, Leonhard Euler, who was Swiss but had to do most of his work in Russia for some reason. A bit of a letdown if you're a Swiss patriot, I suppose, or a Swiss patriot mathematician. And the other thing that's kind of interesting is, like, I think this really, for me, is just almost as profound as Euler's most famous equation, which is e to the I pi plus 1 equals 0. Okay. So thanks to Ivan Sopranov, who I don't really know, and Wikipedia, I borrowed a little bit from your work. But the main point was to use these, to develop these formulas using the SketchUp program, which is sort of like the point of this presentation, really, that you can visualize these things much, much, much clearer. In fact, it almost becomes trivial once you learn how to construct these mathematical objects. In a sense, it's far less mysterious to understand the properties of decahedrons and icosahedrons and octahedrons and so forth. For me, it really kind of crystallizes that in my mind, and I think also it's culturally relevant to subjects like crystallography and so forth, because these are very simple crystal forms, but there are many others. But the underlying crystal structures, the arrangement of the atoms, is also the property of those things also depends on spherical trigonometry. So I think it's useful in that regard too. All right then, that's it.